Alex, you're muted, apparently.
Okay, sorry.
We can hear you now.
Found out how to unmute. Thanks. Am I sharing? Am I screen sharing?
Yes,
All
we can
right,
see your
thanks.
screen.
Okay, thanks for having me, and thank you all for coming. So I'll be talking about corruption, robust reinforcement learning. It's been joint work with Theodoros Likaris, Mark Simsevich, and Van Sun. So I'll start with a sort of a subjective prelude. So it's been a bit of a trend lately to take some insights and some extensions in Ultram Bandits and try to accomplish similar things in reinforcement learning, which usually requires some new ideas. So I found myself doing a bit of that lately, along some themes that I've been pushing for in the bandit land. So one such theme was global constraints, where there was a bunch of work on dynamic pricing with limited supply, and more generally on bandits with knapsacks. And we recently did something along that theme in RL. Another theme was incentives, where you want to incentivize sort of self-interested agents to explore when each one of them selfishly would prefer to exploit. And like recently, we've been thinking about like incentivizing reinforcement learning. I also want to give a shout out to some nice work under Lipschitz assumptions, where one thing you want to do is discretize the space and sort of gradually zoom in on the more interesting regions on that space. And like I've been thinking about that in bandits for a long time, and recently my colleagues did a lot of that in RL, which is very tricky and very cool. So the theme on this talk is what happens if the environment is not quite AAD, but also not quite adversarial. So if it's like, neither of these two extremes, but what if the reality is somewhere in between? Okay, so one nice way of making this more precise is this adversarial corruption model, where the adversary is allowed to corrupt a few rounds. There was a flurry of activity on that in bandits, starting from a paper by Theodoros. And this talk is about, RL with adversarial corruptions. By the way, Theodoros is going to give a 1 hour long talk on this work in a few days in a virtual RL theory seminar. So let me advertise that. It's going to have more details. All right, so let me set up a model. So we consider a standard model of reinforcement learning called episodic RL. So it's like we have a fixed MDP where we know the state space and the action space, but the rewards and transition probabilities are not known to the algorithm. We have k episodes of h steps each. So like the time horizon is effectively k times h steps. So in each episode, we sort of run the MDP. So the algorithm commits to a policy and executes this policy in the MDP for h steps and observes the trajectory of state action reward triples. So policies generally map histories to actions, could be randomized. We assume bandit feedback. In other words, the algorithm does not observe what would have happened if we were in a different state or if the algorithm chose a different action. So that's like a standard model. We're interested in regret, defined in a sort of a standard way. In particular, one can obtain regret that scales as like a root of number of states and number of actions and the time horizon, and it's known to be optimal. By the way, the dependence on h, the number of steps in an episode, is like usually of a sort of a secondary importance in this work. So we will, just leave it at a polynomial and kind of not try to optimize it beyond that. Okay, so that's the standard thing, episodic RL. Now, adversarial corruptions come in a sort of easy way. It's just before each episode, an adversary can come in and corrupt it in an arbitrary way. Now, the number of corrupted episodes is not known in advance. We denote it C throughout. And the goal is to scale, nicely in terms of C, and approximately match the state of art for the case without corruptions. Okay, so what can we do? Oh yeah, and it's important that C is not known in advance. So what can we do? The main result is that essentially we match the optimal regret bound times this C, the number of corrupted episodes. And again, it's not known in advance. By the way, tabular just means that we don't make any structural assumptions, and we just, obtain regret bounds in terms of this S, A, and T. In particular, the adversary is allowed to corrupt transition probabilities. And as it happens, it's the first non-trivial guarantee for RL with non-IAD transitions. And this is like one way in which RL land is much more difficult than the bandit land. Is that in the bandit land, adversarial case, is essentially solved and has been solved for a long time. And in RL land, it's kind of open. So this happens to be the first non-trivial guarantee for RL with non-IAD transitions. And if you go beyond the bandit feedback, so then it's sort of the first computationally efficient guarantee in any feedback model. We also achieve a result for the linear version, which is kind of another standard version of RL, where essentially expected rewards and transition probabilities are linear in the feature vectors. So here, the main point is that the number of states could be very large or even infinite, and we don't depend on it at all. So we match the optimal dependence on T, the time horizon, and the state of our dependence on D, the dimension, even for the IAD case. Moreover, we sort of have a general transformation which takes an algorithm for the IAD environment and makes it robust to corruptions. So we obtain provable guarantees for tabular and linear variants, which are essentially the only two variants of episodic RL when people know how to prove things. But in principle, we expect to obtain provable guarantees for any variant when we know how to analyze optimism under uncertainty in the IAD model. Also, I mean, we could, instantiate an algorithm even if we cannot prove anything. So in particular, our algorithm is can be instantiated in a concrete and meaningful way for deep RL. But of course, we cannot prove anything. So, okay, a good time to talk a bit about prior work. So the way I think about it, there are two stories, one from bandits and one from episodic RL that converge nicely to this project. So the bandit story is about stochastic versus adversarial. So there were these classic papers that solved either version separately about 2 decades ago. Then Bobek and I came along and kind of obtained the best of both worlds, which is this one algorithm which achieves approximately optimal regret for either environment without knowing which environment you're in. And there's been some activity on improving and refining these bounds. Then it was natural to ask about intermediate regimes. I mean, what if the world is neither really nice, nor really bad, but somewhere in between stochastic and adversarial? And one, nice way of thinking about it was adversarial corruptions. So that work started with the Licorice Mirokny Paes-Lemme paper, and their regret bounds were improved and refined in 2 subsequent papers, and there were extensions in several other directions in bandits. So, okay, the story in the episodic RL is a little different. So there has been a lot of activity on the stochastic version over the past decade, and like, I cannot possibly cite all of it. In particular, we now have worst case optimal regret rates, and we have instance dependent regret rates. And there's been some sort of active line of work on adversarial rewards. But, adversarial version is sort of active, but, far from being well understood. There is a lot more to be done there. Okay, in particular, let me talk about two specific ideas that are from prior work that are very relevant to this project. It's kind of two standard well-known ways to resolve uncertainty. One is active sets, and another is optimism. So active sets is basically we look at the data, we compile the set of actions that could still plausibly be optimal given the current data. We call it active set, and we choose uniformly or near uniformly from that set. So optimism is that, like, I'm kind of informally defining it. We pick an alternative with the best optimistic estimate, which means like the most favorable estimate, which is still consistent with the data. So active sets stuff, it works for bandits. And in fact, it works for corruption robust bandits in the sense that it, this idea underlies the corruption robust algorithm in Licorice Miroknir by Slema paper, but it fails miserably for reinforcement learning. So in fact, we can prove that, like, any reasonable way you could define active sets is gonna suffer, and like if you choose uniformly from them, you will suffer a very high regret. Okay, optimism, on the other hand, it works really nicely for RL. In particular, like sort of a standard and natural way of doing optimism in RL is something called optimistic value iteration. It works great, and it sort of underlies most of episodic RL algorithms in the literature, and it works great, but it fails for corruptions, even for bandits, and it's sort of easy to see. I mean, think about like an adversary that comes in and assigns a reward of 0 every time the algorithm tries to pick the arm that is actually the best arm. Then if you do it log t times, then you would fool the algorithm into thinking it's a very bad arm. So anyway, the point is that here you have two techniques. So active sets works great in the bandit land, fails for RL. I mean, works well for corruptions, fails for RL. And optimism works great for RL, but fails for corruptions. So, okay, in the rest of the talk, I'll sort of quickly go over the main ideas. So the starting idea is sort of marry optimistic value iteration with active sets. And I'll explain it kind of quickly, kind of one by one. So value iteration is just a very standard, well-known way to compute the best policy in the known MDP using dynamic programming. So you sort of iterate from like last episode to the first episode, and you keep like updating Q function and V function and the policy. So that's like very standard. Then optimistic value iteration is that, well, you don't know reward and transition probabilities. So instead you plug in like optimistic estimates of the rewards, and this way you have optimistic estimates of the Qs and so forth. Okay, what we do is we compute not only upper confidence bounds, but lower confidence bounds on the Q function using pessimistic reward estimates. And then we use that to essentially recompute active sets. And then when we update the policy, we restrict what we do to the active sets. So this is kind of like the base algorithm and what we do. And then we also need to use sort of both local data, which is like data from this algorithm, and like global data. And like I will explain what that is in the next slide. And we use sort of both data sets to compute UCBs and LCBs. So anyway, that's like on a high level, the base algorithm and what we do. So the full algorithm is a sort of a system of these base learners where each base learner runs a separate instance of the base algorithm. And it is robust against a given level of corruption, which kind of scales exponentially. So like local data is like data assigned to this base learner. And we also have like global data, which is a union of data from like all base learners. And we do need global data essentially because of the trajectory mismatches. I mean, different base learners may traverse different trajectories in the state space. So we start with the least robust, like really non-robust base learner, and then at each step of each episode, we may randomly switch to a more robust base learner. And we use sort of a carefully chosen but data-independent probabilities for the switches. And the point is to ensure that we have a sufficient probability, like at any step, we have a sufficient probability of switching to a more robust base learner for the rest of the episode. That's sort of the key point in the algorithm. And the data inside a given episode is assigned to the last and the most robust base learner that we went to in this episode. So the high-level idea here is that more robust base learners, in some sense, supervise the less robust base learners through this global data, which is shared among everybody. Okay, so it's a 100-page long paper, and I have exactly one slide to summarize the analysis. So I'll just go over some key ideas. So, I mean, we have a general framework to analyze these base learners with active sets. And in particular, like, base learners could do something which is not UCB selection or not quite UCB selection. And the point is like how to analyze that. So we look at Bellman errors, which is essentially, the error inherent in the Bellman update. It's like a standard thing. I won't go into that. The point here is that like we have a regret decomposition where we express regret in terms of some expression in terms of the Bellman errors, and this allows us to plug in a sort of analysis from the prior work in a nice way. So the key issue is that, okay, we have something which is nice maybe, but we only really know how to bound regret for UCB policies because like essentially UCB policies give us sufficient exploration. So somehow we need to compare whatever we do to whatever a UCB policy does. So here's the way we think about it. Okay, we say, okay, what if we start with like whatever we do, and then we switch to a UCB policy after some given step H. So let's call it policy pi prime. Okay, now let's look at the occupancy measures of these two policies after some future step tau. Well, now let's compare these two occupancy measures. So let's look at the maximal ratio of these two occupancy measures where the max is taken over everything, over this H and over this tau and over states and over actions. So it's like, how much can possibly policy pi star be different from the original policy pi? So in other ways, you look at it as like a change of measure. We're like want to change, one occupancy measure with the other measure, and like we pay a penalty, and we are trying to like upper bound that penalty. So that is somehow the key quantity in the analysis. This is this ratio. So anyway, that's all I want to say about analysis, and like Artiodoros is gonna give more details in the longer talk. I do want to take a step back and point out that there is something going on which is perhaps more general than corruption robustness. Namely, we have this RL challenge, how to inject enough exploration into some, some complex behavior. For example, behavior that ensures corruption robustness. So optimism under uncertainty happens to be the best hammer that we got. And we have this general design principle that we randomly switch to like a more reliable version of the optimistic behavior, for example, to a more robust base learner. And we have a general framework for analyzing, these algorithms. In fact, as a simple proof of concept, we provide a new algorithm for the stochastic episodic RL that is kind of the standard version without corruptions, that where we start with active sets and uniform exploration, and we inject a little optimism to ensure enough exploration, and we obtain optimal regret. So it's not a new result, it's just a proof of concept. The point is that this machinery, we apply this machinery to corruption robustness, but it could potentially be applicable to other domains. Okay, so let me conclude with some extensions and open questions. So we also have results for instance-dependent regret, which is kind of similar to instance-dependent regret for bandits, in that we have like logarithmic regret, as long as some notion of a gap is small for like, appropriately defined notion of a gap. So in particular, we match the state of art for the AID case for the constant level of corruptions. Now, the main open question is about the dependence on C, on the number of corrupted episodes. So in our work, it is linear. And well, can we make it better? And there are sort of several ways to like ask this question. So one is like, can we make it like linear but additive rather than like linear and multiplicative? Or can we obtain non-trivial guarantees for C greater than root C? Or can we obtain like sublinear dependence on C, ideally like root of C? And like one way to make our lives easier here, which may help, is that like, what if we only count regret for non-corrupted rounds? So the answer to all these questions is like yes in the bandit land. So maybe one could do some of that in the RL land, maybe not. Okay, so that's about it. And let me remind you guys again that, I'll come to the Dersis talk, and there is a link to the paper. So thank you very much.
Great, thank you, Alex. We have a few minutes before the next speaker needs to start. So if anyone would like to ask any questions, now would be a good time.
Do I understand that there is no lower bound at all for this corruption framework, or are there any lower bound?
So like no lower bound is specific to RL.
Okay, for bandits?
There is something for bandits, but it's like, it is subtle and tricky. So, and like, I may be messing it up. One thing that I remember is that like, if you want like better than log squared T regret in the stochastic case, then you're doomed to like linear dependence on the corruption. But there was a subtlety which I don't remember. I think that also required high probability guarantees, not expected guarantees. And there's a subtlety that I usually get wrong, like, sorry, okay, well, let's leave it at that. Right.
Can I ask a question? Oh, go on.
Oh, sorry, there is a root C result, but if I remember correctly, and I may be messing it up slightly, it's for pseudo regret, and it assumes that like you don't count regret for the non-corrupted rounds. But if I'm messing it up, then like correct me in the chat.
Can I ask a quick question?
Yeah.
So for the linear MDP case, are you paying for the number of actions?
Oh yeah. So that's one way in which we are not matching the state of alert. I was, yeah. So hold on, let me come back to it. So yeah. So right. So we pay for the number of. So we pay for the number of actions, but not for the number of states. So
right. And do you think this is like fundamental somehow? Because I think you can do action elimination for linear bandits without paying.
So I mean, without corruptions, you can get rid of it. It's like we don't know how to do it. With corruptions, I don't know. I don't have an opinion on whether it's fundamental.
Okay, thanks.
I don't know. It's just we cannot do it.
Max, I think you had a question, or you raised your hand.
No, oh, that was an accident. Sorry.
Okay, no worries. Okay, well, I actually had one question as well. What exactly is the corruption model you're using?
Right. So, So the adversary, in the beginning of each episode, the adversary can decide whether to corrupt this episode, and if it corrupts this episode, it can do it in an arbitrary way. It could corrupt, rewards or transitions in an arbitrary way. And we only count the total number of corrupted episodes.
I see. And there's no bound.
That number is, excuse me?
There's no bound on the side of the corruption. They could be arbitrarily large, or is it the cost, say, still assumed to be bounded?
So we don't know in advance how large it is. And, we pay for that in regret. So in a particular, that bound is vacuous if C is greater than root T. And not vacuous otherwise. So.
Good, thank you. We maybe have time for one more quick question if anyone has something.
Okay, let me stop sharing.
Oh, so Theodorus raised a Q&A. Maybe Csaba already read it, but he's talking about the lower bounds. So he says square root C for pseudo regret is achievable for pseudo regret for the corrupted objective. This is in Zimmert and Selden. C is necessary if you want less than log squared T for high probability for the corrupted objective. This is in Lycoris, Marocni, plus Lemme. And C is necessary for the uncorrupted objective. Thanks, Theodorus.
Yeah, thank you. Well, in that case, okay, great, Dan. I see you've already started presenting. Please welcome our next speaker, Daniel Rousseau, who is an assistant professor at Columbia Business School. He is also